All right, let's go ahead and get started. I do want to welcome you back to Unit 9. This is Stoichiometry. And we said that stoichiometry was when we looked at the relationships between reactants and products in a balanced chemical reaction. And from one amount, we could determine something else, right? But we looked at so far only at mole-to-mole relationships, either using kind of intuition in just our head, or we've looked at using dimensional analysis to be able to calculate how many moles we're going to get, or how many moles we need to start with. But what we want to do now in this reaction is we want to take a look at gram to mole relationships. So let's take a look at this example. This is for the reaction of lead nitrate and 2 moles of potassium iodide. We get lead iodide and potassium nitrate, okay? And it is a 1 to 2 to 1 to 2 mole to mole to mole relationship, right? First of all, let me ask this question. Folks, we've talked about 5 different types of chemical reactions in our chemical reactions unit. And what I want to ask you is, what kind of reaction is this? Is it a synthesis, a decomposition, a single replacement, a double replacement, or a combustion reaction? Those were the 5. Which one is it? Well, yeah, it's a double replacement reaction, right? We have 2 ionic compounds that are going to switch. So lead getting together with iodine, potassium with nitrate. And in that process, we formed a precipitate, right? So again, in terms of moles, we've got a 1 to 2. Let me underline that. 1 to 2 to 1 to 2 mole to mole to mole to mole relationship. So now what I want to do is I want to take and make sure that I know what I'm being asked, right? It says how many moles of lead iodide can be produced. So I'm going to put question mark moles, just like that. How many moles of lead iodide can be produced from 2.4 grams of lead nitrate? So we're going to say 2.4 grams of this lead nitrate. So we make it explicit exactly what we started with and what we're looking for, so that way there's no confusion. All right. So here we go. What do you want to know? Write what you want to know and place it over 1 to hold the place. Okay. Convert the grams of what is known to moles immediately. So remember this. When you're doing stoichiometry and you're given a number of grams, either for, well, let's say the compound like this, you're going to convert those grams to moles immediately. That's the first thing you're going to do even before you look at the balanced reaction. So I was given this number of 2.4 grams of lead nitrate. I'm going to put that over 1, and right now, before I do anything else, I'm going to convert that to moles. This 331.22 grams of lead nitrate I obtained by adding up the atomic weights of lead, 2 nitrogens. Why 2 nitrogens? Well, because there's a 2 right there. And 6 oxygens, because 3 times 2 is 6, right? 3 times 2 is 6. So when I add that all up, you check me, I get 331.22 grams of lead nitrate. So this and this are going to cancel away, and I'm left with moles of lead nitrate. That's what I want. So what do I do with these two numbers? Do I multiply or divide them? Well, obviously I'm going to divide them because of the fact that I've got one on top, one on bottom. I'm going to divide, right? By the way, I've got 2 significant digits here on top. I've got, what, 5 on the bottom? I'm going to take the lesser of the 2 because I'm dividing. So I get 0.0072 moles of lead nitrate, right? So now I know how many moles of lead nitrate I have, but I'm not done yet by any means. But at least I've gotten that far. So I'm going to start with that. So what I'm going to do now is call a mole-to-mole bridge, right? I'm going to do a mole-to-mole bridge from the moles of the known to the moles of the unknown. The coefficients in the balanced reaction are used in this bridge. So let me show you where the bridge is in the balanced reaction. So I'm starting with lead nitrate and potassium iodide, and I'm ending up with lead iodide and potassium nitrate. But here's where the bridge is, right here. I'm going from what I know to what I'm looking for. That is the bridge. What I know to what I'm looking for. It's a 1-to-1 mole-to-mole relationship, right? A 1-to-1 mole-to-mole relationship. So I'm going to use that in my calculations. So I'm going to start with what I know, or what I've calculated, I should say, which is 0.0072 moles of lead nitrate. Put it over 1 times, and here's the relationship. 1 mole of potassium iodide to 1 mole of potassium nitrate, right? So now this and this are going to cancel away, and I'm going to be left with 0.0072 moles of lead iodide. Now you may say, well, that was a waste of time. Anytime you multiply by 1 and divide by 1, you're just going to get the same number. No, I don't really consider it a waste of time. I think that you need to go through the procedure correctly on every problem and try to avoid doing things in your head, especially when a grader is going to be looking at it and determining what it is that you did, because they're going to want to know how you arrived at your answer. Or you could just do it all in one string. So you could start with a 2.4 grams of lead nitrate, put that over 1, and then convert that to moles right here. That's now in moles of lead nitrate, and then just in one complete strand, multiply again by 1 mole to 1 mole ratio. But again, I get 0.0072 moles of potassium iodide. Okay, 0.0072 moles of potassium iodide. So that's it. That's my answer, right? I've answered the question that I was looking for. Let's just go one more time to the balance reaction to make sure that that's where my question mark was, right? So if I go to the balance reaction, yep, there it is. Question mark in moles of the lead iodide, and that's exactly what I calculated, right? So I'm confident in my answer, right? I'm confident in my answer. All right, now, we've gone from moles to moles. We've gone from grams to moles and moles to grams. But now what we want to do is we want to go all the way from grams of known to grams of unknown, right? It's not difficult at all. All right, this is about as difficult as it's going to get, but even then, it's not really difficult at all. All right, if you can do this one, you can do just about anything with regard to stoichiometry. All right, so here we go. Here's an example. It says for the reaction of 1 SO3 plus 1 H2O, we get 1 H2SO4. That's sulfuric acid. And by the way, let's just take this opportunity to look at or ask the question, what type of reaction is this? Is it synthesis, decomposition, single replacement, double replacement, or combustion? Well, it's synthesis, isn't it? We have two things that are coming together to form one, so it's a synthesis reaction, right? Synthesis reaction. All right, so how many grams of H2SO4 are expected to be formed from the 12.3 grams of SO3? So again, I highly recommend that when you're doing these problems that you write over the problem, right on top of it, right? How many grams of H2SO4 are expected to be formed? So I'm going to put question mark, and not just a question mark, but question mark grams, because it's not going to be good enough for me to to answer the question in moles. I need to know it in grams. And so it says formed from 12.3 grams of SO3, so I'm going to put 12.3 right here. So 12.3, but not just 12.3, 12.3 grams. So it's now explicit. I know exactly what I'm starting with and what I'm ending up with, right? Okay, great. So how do we do this problem? How do we find the solution? Well, what we're going to do is we're going to start with what we know. We've got 12.3 grams of SO3. I was given that in the problem. Over 1 times 1 mole of it. Remember, convert grams to moles, anything to moles immediately, all right? Anything, if we're later on, if we're talking in the gas unit about liters, we're not worried about that right now, but later on, convert liters to moles. Convert anything you have to moles immediately, because this is a mole to mole to mole relationship, not a gram to gram to gram relationship or a liter to liter to liter relationship. So you want to make sure that you convert to grams immediately. So we get 12.3 grams of SO3 over 1 times 1 mole of SO3 per 80.0 grams of SO3. Where did I get the 80.7? Well, I just added up sulfur and 3 oxygens, and that gave me that number. By the way, check me on that, please. By the way, I wanted to 2 significant digits, okay? In my classroom, if you're in another classroom, then just consult with your teacher. But if you're in my classroom in San Antonio, Texas, I want you going to 2 significant digits, 2 numbers to the right of the decimal, I should say. Let me say that. 2 numbers to the right of the decimal, off of the periodic table. All right, that's per mole, right? So now I'm left with moles of SO3. Moles of SO3 here, moles of H2SO4 here. What's the relationship? It's a 1-to-1 relationship, right? A 1-to-1 relationship between SO3 and H2SO4. So this now is going to cancel with this, and I'm left with moles of H2SO4. Am I done? No, I'm not done. Remember, I'm looking for grams. Look at the balanced reaction. Look what you wrote there. I'm looking for grams. So there's one more step. Times 98.09 grams of H2SO4 per mole of H2SO4. And this will cancel with this, and look what I'm left with. 15.07 grams of H2SO4. Now, notice that this last step gets us back to exactly where we want to be, which is grams. Okay? All right. Folks, we're pretty much done then. Remember I said that if gram to gram relationships was as hard as it gets, well, then that's as hard as it gets with regard to stoichiometry, right? But what we want to do now is we want to take a look at some other skills that are going to be important to us. One of them is determining what we call limiting and excess reactants. Limiting and excess reactants. So when two reactants combine to form products, one of the reactants limits the amount of products that can be formed while the other is in excess. Let me give an analogy. And by the way, this analogy involves my favorite topic in the whole world, which is not chemistry, actually. It's food. All right? Just to be honest with you, I'm revealing something about me personally now. I love food. All right? And one of the things that I like to eat are peanut butter and jelly sandwiches. And I hope you do too. Let's take this analogy. Let's just say, for example, that you're having a peanut butter and jelly sandwich party at your house. Okay? You're having a peanut butter and jelly sandwich party this afternoon at your house. And you want to know how many people you can invite to the peanut butter and jelly sandwich party. Okay? How do we go about this? Okay, follow me on this now. I know you're saying, what does this have to do with chemistry? Just listen to what I'm going to say, and you're going to see in just a moment what it has to do with chemistry. Okay? All right, so you're trying to figure out how many people that you can invite to this peanut butter and jelly sandwich party, right? And so here's what happens. You have a full jar of peanut butter. I mean, it's brand new. The cap hasn't even been removed for the first time yet. There's still that aluminum film on top. So you've got plenty of peanut butter, right? Then you look in the cupboard, you see there's plenty of jelly. Or look in the refrigerator, see there's plenty of jelly as well, right? So that's not a problem. Not one jar, there's 2 jars of jelly in the refrigerator, right? So that's not a problem. But you now look in the cupboard and there's only 6 slices of bread, right? There's only total 6 slices of bread, not including the ends, which nobody eats anyway, okay? All right. How many people can you invite to your party? You can only invite, well, if you're going to eat one of the peanut butter and jelly sandwiches, and I would imagine you would be doing that, I would, then you can only invite 2 people because you can only make 3 peanut butter and jelly sandwiches, correct? In other words, the bread is what's limiting you. The bread is the limiting reactant. You can only produce 3 peanut butter and jelly sandwiches total, right? All right. Now, some of you are going to say, well, what if you make a peanut butter and jelly sandwich from 1 sheet of bread? Don't be ridiculous, okay? All right, let's not even talk about those kinds of things. Peanut butter and jelly sandwiches should have 2 pieces of bread, one on either side, one for the peanut butter side, one for the jelly side. So let's not talk about 1 bread peanut butter and jelly sandwich. It's ridiculous. All right, so that's that. That's what we mean by limiting an excess reactants. Well, in the same way, for a chemical reaction, you can only have, if you have a reactant and you have a product, right? Then, or let's say you have 2 reactants and 2 products. One of the reactants is going to run out first. Just like the bread ran out first for your peanut butter and jelly sandwich party, one of the reactants is going to run out before the other. We call that one the limiting reactant. Okay, the limiting reactant. And we call the other one the excess reactant. Okay, the excess reactant, just like that. All right. Okay, folks, I think that's going to do it for this one. So on the next one, I'm going to talk to you a little bit about a reaction. But before I do, I'm going to make myself a sandwich because I'm pretty hungry now. All right, I'll talk to you later. Bye.